Hi everyone, good evening. So today we are going to do, this, the discussion on Gate 2023 analog circuit questions. Okay, from electronics and communication, as far as the official key also has been released, right? So as we can see here, today's session will be on electronics and communication engineering, and the subject will be analog circuit. Okay, and we will also talk about the how many questions we have got this year. Okay, so you will find that how we approach to the problem, okay, first of all, and we will discuss the solution in detail, right? So this was the section B, okay, and the subject was analog. You see here, one of the very important subject for electronics and communication, and it is regarded as core subject, okay. One can go for analog circuit or digital circuit after cracking gate examination, and lot of opportunities are there in front of us if you're good at playing with the circuit, right? So as you can see, for 1 mark, there were two questions, and for 2 marks, there were four questions. So if you add them, right, so 2 plus 8, that is 10. So this year, for 10 marks, they have maintained the same consistency, right? Each year you will find 10 mark questions, from this subject, and this is one of the core subject. And okay, so you will also learn how to play with this subject, right? Okay. So this was a question, okay, asked in the gate 2023, and this question already I discussed in our, in my regular classroom. Okay, so whenever op-amp problem will be given in your exam, always keep in mind whenever question will be asked from op-amp. Okay, so first of all you have to identify this circuit. Okay, because there are three op-amps. Okay, so you have to identify that what is the purpose of this circuit, and what is the name of this circuit. Okay, so you see here, this is a op-amp and they haven't mentioned anything here, right? The V out upon V in of the circuit shown below, we have to find output upon input, right? This is the input connected here, and this is the output taken from the third op-amp. Okay, so they haven't mentioned anything, so you have to consider that the op-amp, all op-amps are ideal op-amp. Okay, that you have to understand. And operational amplifier is one of the versatile structure that you have to keep in mind. Most widely used structure in analog industries. Okay, in VLSI industries. Okay, so so you see here, and whatever we will do, we are not going to get into the op-amp. We will be analyzing this op-amp circuit just by following these resistances. Okay, whatever resistances are connected around this, that is the beauty of op-amp, right? Okay, so you see this is where we have connected the input here. You see, this is a negative terminal and this is a positive terminal. Okay, so the input is connected at negative terminal, okay, via R1. Okay, you see guys, and this input is this positive terminal is grounded, so you can say that this is a inverting amplifier. Okay, inverting amplifier. Okay, inverting amplifier. So if I talk about inverting amplifier, okay, so suppose this is minus and this is plus. So whenever we talk about inverting amplifier, so always keep in mind the input will be given to negative terminal always. Okay, and via feedback, this is the output. Output is connected via feedback. Okay, via some resistance, and this resistance we have been given is R2, right? So this is R2 and this is R1, right? And this is grounded. Okay, so you can directly write the output. Okay, so we must know that what will be the output of this op-amp. So it should be minus R2 by R1 times V in. Okay, this result you should know. Okay, if you have completed analog circuit properly, so you should know this result first of all. Okay, and how we are getting this result, when this is our ideal op amp, so this, if this is a potential which is at zero, right, you can say this will be also at zero because of virtual ground concept. Okay, if op amp is ideal, so we can use the concept called virtual ground. Why we are using virtual ground here, why, what is the reason behind that, we will discuss in our regular classes. Okay, in the op amp circuit, there is a chance that KCL can be violated, right? So you see here, if you're going to apply KCL at this point, right, so you can't apply KCL because the output current of the op amp is unknown always, right? You see, there is no current, okay, until or unless they have given in the question. So we can't apply KCL here. We can apply only KCL at this point because all the currents are known, right? Here, op-amp does not take any current, that you have to keep in mind. So that is the reason, as we are not able to apply KCL at output, right? So we replace. Then how we are going to analyze the op-amp circuit, right? So we always consider this virtual sort concept so that analysis become easier, right? That these are the arguments which we make during our classroom, right? So this is the first op-amp, which is the inverting amplifier. So you can say that at this terminal, output terminal 1, you can say this is going to be the output. And what will be output here? Directly you can write output. So V naught 1 will be equal to minus R2 by R1 times V in, right? This is what the output 1, right? Now you can find output 2 as well here, okay? Output 2. So as you can see where input is connected, this input is common to both op-amp, okay? So input is connected at the positive terminal this time, right? Okay, and this negative terminal is grounded, but it is not directly grounded. It is grounded via R1. Okay, so it is a non-inverting amplifier. And let me sketch here the non-inverting amplifier as well. So you see this is minus and this is plus, and this time input is connected at positive terminal, right? Like this V in. Okay, and there is a resistance and feedback resistance is there, and this is your V out 2, and this was V out 1. Okay, and this is grounded, right? So again you can see what resistance they R1 and R2. Okay, so this is R2 and this is R1, right? So as I'm explaining, so we are taking a little time, but during the examination, you have to solve the question quickly, so you can solve this question within 30 to 40 seconds. So you can see here, as you know, op-amp does not take any current, right? And the voltage will be here same because of virtual short concept, that is V in. And these R2 and R1 will be in series. So you can apply the voltage division rule, as we know that suppose this is R2 and this is R1, right? You needless to apply KCL here, right? Just consider like this V out 2, and you know the voltage across this is what? V in here because of virtual sort V in, right? So you can apply the voltage division rule. So here it will be in terms of V out 2 times R1 by R1 plus R2, right? Which is equal to V in, that you can equate directly. So you will get V out 2, right? So V out 2 you will get as, it will be 1 plus R2 by R1 times V in. So till this point, everybody understood, okay? So we are not applying. You can also solve this question by applying KCL here, right? Writing, but voltage division rule will give you quick answer, okay? So V out 2 you have got here. This is V out 2. Now let's get back to the circuit. So as you can see, both inputs are connected at negative terminal of the op amp, right? And two inputs are connected. One is this, one is this. Okay. So you can consider this is a adder circuit. Okay, adder circuit. This is the adder circuit. These kind of operation we do as we call operational amplifier. So these are the linear operation we do using op amp. So this is adder circuit because we are adding two inputs here in the same terminal. Okay, so as they have given two inputs, right? So you can again apply what? You can again apply the superposition. You have to take one input and find the output, take one input, find the output, right? Okay, then you can sum them up. That is called the superposition, right? So as you can see, this is again the inverting amplifier. Okay, inverting amplifier. So output will be what? Suppose this is V naught 1, this is V naught 2. So output will be, because of V naught 1, it will be minus R4 by R3. Okay, minus R4 by R3, right? Times V naught 1. Okay, again you just turn this off, right? You have to make this V naught 1 grounded, right? So next output will be R4 by R3 times V naught 2. This is by superposition we have written directly, right? Okay, now you can plug this V naught 2. V naught 2 we have already got, that is R2 by R1 times V in. Okay, so you can take also common this R4 by R3. Okay, so let me go ahead and plug all these values. Okay. So we will plug here. Okay. So you can plug. So what will be happening next? You can take minus R4 by R3 common. Right? So this is V naught 1 minus, and this will be plus V naught 2. Okay. I believe this is fine for everyone. So now minus R4 by R3. Okay. V naught 1 is what? That is minus R2 by R1 times V in. Okay. And then you can put V naught 2 as well. Right. So V naught 2 will be what? V in. Okay. So you write here that is V in. Okay. V in. And then this there will be one more V R2 by R1 times V in. Okay. So this is plus R2 by R1 times V in. Okay, right. So you see this and this are getting, these two terms are getting cancelled, right? So what you're getting exactly as a output, as V naught, V out is going to be minus R4 by R3 times V in, right? V. So this is going to be your output, and you can take this guy gain, because they are asking the gain. Okay, V out by V in. So it will be R3 by R4 by R3. Okay, R4 by R3. So I believe this is fine for everyone. So which option is correct here, guys? Can you comment? Which option is correct? Minus R4 by R3. So option A is going to be correct, and according to the official key also R minus R4 by R3 is correct. So everybody understood this now? Okay. Yes, great. So see, in the regular classroom we will discuss all these things, right? But yeah, so yes, okay. So you can identify the moment you see the circuit, identify the circuit, okay? Because nowadays questions are being asked where you need to know, okay, what kind of circuit they have given. If you know the property of the circuit, you know the results of the circuit, you can quickly solve the question. Otherwise, this big 3 op amp might confuse you, right? You will think that, okay, sir might have told you the KCL you have to apply to analyze the op amp, okay? Then you will apply KCL, find out V out 1, V out 2, and then again, right? So it will take time. But how I have written this output directly? By superposition. By superposition. And also one more thing is there, as it is a adder circuit, so this will add to, you can see here, this is being added by certain factor minus R4 by R3. Understood, guys? Okay. So let's go to next question. Okay. So this was all about the mathematics behind, okay, the concept behind solving this question. Yeah. Again, this question was asked, one of the very good question, and this question was directly from our notes. Okay, whatever we have taught in the class, right? So in the circuit below, you see the voltage VL. Okay, the voltage VL is, you have to find VL, and this VL they are asking. Okay, plus minus. Whenever voltage is given, so you have to put plus minus always, right? So you have to find the voltage across this 1K ohm resistance, right? So how can you find 1K ohm voltage across that? You know already the resistance, right? So you need to find the current here. Okay, if you know the current, then VL is going to be what? VL will be I times 1K ohm, right? So if you know the current here, okay, so you can find out easily, right? But by looking at the circuit, what you are able to, what you have to identify here is this is a current mirror, okay, MOSFET based current mirror, okay. So here we are using MOSFETs, okay, and what we are doing, these are the P MOSFET, okay. This is P MOSFET, this is P MOSFET, okay. Why we are saying this is a P, okay, P channel MOSFET? Because this is source basically, okay. This is source and this is gate and this is drain, okay. Because the maximum potential is connected here, right? That you have to identify. Yeah. That's why it is a P channel MOSFET. Yeah. So now you see this is a current mirror, but they have different W by L ratio. Whenever gate and drain are sorted, so always consider that op amp, this MOSFET is in saturation, and we must know the current equation in case of in case of saturation region, right? So 1 by 2 You can say this is going to be what, as far as this p channel MOSFET is concerned, or you can just write the equation here, right? So mu p cux, right, w by l, right, vsg minus vt whole square, right? That you can, okay, write here like this. Just put the mod, okay. Or you can also write for n channel MOSFET, that is 1 by 2, okay, mu n cux w by l vgs minus vt whole square. So what you have to observe here is that you have to observe that this drain current is directly proportional to w by l, right? Your drain current is proportional to w by l, okay. And what is the property of current mirror, guys? If these all the parameters are matching of these two transistors, okay, so whatever current is flowing through this transistor, the same current will flow through this transistor, right? Okay, this transistor which is connected here, okay, and as this transistor and this transistor are in series, okay, so same current will flow. But as you can see, W by L ratios, these are known as aspect ratio, width upon length ratio, right? So they are not same, okay. This is 10 times greater than this W by L, okay. So your current will also be 10 times greater, okay. So as you can see, you can consider this is ID1, okay, and you are finding here, you can say this is ID2, right? So let me apply the proportionality rule here. So ID2 by ID1 will be what? W by L 2 upon W by L1, okay. So as you can see, this is given as 1 and this is 10. So your ID2 will be what? ID2 will be 10 times of 1 milliampere, right? So this is 10 milliampere. So you don't have to write in the exam these many things, okay? Just you have to understand that ID is proportional to what? ID is proportional to W by L. So this will be what? This will be 10 milliampere, okay? So the same current will flow here as well. This is 10 milliampere, okay. Now they have connected here the n channel MOSFET based current mirror, right? So again, current mirror means what? If W by L ratios are matching, right? So whatever current 1 milliampere is flowing, the same current will flow here as well. And again, you see this is W by L equal to 7, and these two transistors are connected in what? Connected in parallel, okay. So you have to find the current through this transistor as well with respect to the reference transistor. This is reference current, right, in case of current mirror. So what is going to be the current here? This is 7 and this W by L ratio is 1. So the current will be flowing here is what? 7 times the I reference. You can say this is 7 milliampere here, okay, via this transistor, okay. And now, as you can see, this is 10, and now WL by W upon L ratio, okay, this aspect ratio has got decreased, right? It means what will happen here is that here 10 milliampere current is flowing, so current will be reduced here as well, okay. So what will be current here? 5 by 10 into, this is, you can consider this is ID1 again, this is ID2, right? So 5 by 10 into 10 milliampere, right? What we will write? 5 by 10 into 10 milliampere, right? So this is cancelling. So what is current here? 5 milliampere, right? Now you can apply the KCL at this point because the same current will be flowing here 7 milliampere, and you have to find I, okay? So one current is going 5 milliampere, one current is coming to the node, that is 7 milliampere, and I is going away, right? So you can say apply KCL, okay, so by KCL, 7 milliampere is coming and I plus 5 milliampere is outgoing, okay. So you can say I is going to be what? 2 milliampere, right? You got I as 2 milliampere. Now you know milli and kilo. If you take the product here, kilo is given and you got milli here, right? So 2 into 1, because milli kilo get cancelled. So what will be the answer, guys? Can somebody now tell me? As you have got I through this 1K resistance. So it is going to be VL will be what? VL will be 2 milliampere into 1K, that is 2 volt. Yeah. So I hope everybody understood this concept, right? Okay. So please write on a chat box. Yeah. So this question was not that difficult if you know the property, if you know the relation here, right, and if you know the proportionality, right, because as a fresher, what we don't understand that suppose x is proportional to y, right? So if x2 by x1 should is there, then y2 by y1 should be written, okay. And if x is proportional to 1 upon y, so you should write x2 by x1 equal to what? Y1 by y2, right? These kind of a relation you should know, okay. Then only you can solve this kind of question. So I believe, according to the answer key also, this is correct question, right? So 2 mark you can easily get, okay, and it will take around 30 to 40 seconds, okay, in the exam, because you have to take care of all the transistors. Don't make mistake, okay, and don't forget here. You see, whenever W by L ratio is increasing, the current will increase, okay. Whenever the current mirror current, okay, and uh, whenever W by L ratio is here, you see 10 out. Earlier it was 10, now it is 5, so current has got decreased again, right? Okay. So this was one of my favorite question, and all of my students have done this question as well, right? And I have discussed everything in detail in the classroom. Okay. In fact, in the first class only, I discussed this kind of question. I mean, this kind of a model, right? At least these you know, four kind of a controlled source, and I claim that to model an amplifier, we need dependent current source, dependent voltage source. Okay, in fact, you can say dependent sources, right? So one of the major application of dependent sources are what? To model an amplifier. Okay, if you want to model an amplifier, so you have to use dependent sources, right? And there can be four kind of dependent sources: voltage control voltage control current control current source, and current control current source, right? So if somebody has attended my first session, they will be able to solve this question, right? Okay. So in the circuit shown below, V1 and V2 are biased voltage. Okay. So you see here, these are the biased voltage. Okay. And while doing the AC analysis, you have to make them ground, AC ground. Based on the input and output impedances, the circuit we have says, okay. So suppose if in the question they have given voltage amplifier, so what will be the input resistance? Input resistance will be high and output resistance will be low. In case of current amplifier, always keep in mind input resistance will be low and output resistance will be high. So these kind of concepts I discussed in the first class under the topic amplifier modeling, right? So suppose there is a VCVS, I mean, input is voltage, output is voltage. So input resistance here I'm writing and output resistance I'm writing here. Okay. I will come back to this circuit, wait, okay, in a while. So this is high and this is low, okay. And current control current source means current amplifier, so it is low and it is high. If output is, if output is current, okay, and input is voltage, right? Voltage control current source, right? It means it is known as trans conductance amplifier. So input resistance will be high and output resistance will be high. So these kind of a property I tell in the class, right? So if input is current means current control and output is voltage, so VS voltage source we will use. So it should be low. Okay, so these are the four kind of amplifier. In fact, four kind of dependent sources. Okay, so major application of dependent sources is what? Major application of dependent sources is to model an amplifier. That you have to keep in mind. Wherever you see the dependent sources, you have to recall the amplifier. Yes. Now come to the circuit. So you see, guys, while doing the AC analysis, because we have to find input resistance and output resistance, based on that, we have to claim here. If input resistance will be low and output resistance will be high, so we will call current control current source. This is a current control current source. Now, while doing the AC analysis, we will make it ground and we will make it ground, right? And we have to find what? We have to find the output resistance. Okay, means we have to put Vx and this is Ix, and we have to make this guy you know sorted also. Input of this will be sorted and this is also grounded. Okay, you see, guys. So whenever these two transistors, these two terminal of this PMOS here, you see this is source and this is you know okay, so they have been sorted. Okay, so what you can say, this this transistor we have like an active load, you can say. Okay, okay, simply we have like an active load. Okay, and this you can see here, this source is degenerated. Okay, source terminal is degenerated. This is R1, right? So whenever, suppose there is no R1, right? Whenever R1 is not present, so your output resistance will be R not only, right? But then whenever this source resistance, source terminal is degenerated, what is the meaning of degeneration? Suppose I'm taking one circuit, right? I'm taking one circuit here. Common source amplifier I'm taking. Okay, here the load is passive this time, right? So this time I am not connecting any resistance at source. Okay, terminal, right? This is drain, this is gate, and this is source. So no resistance is connected, right? No source degeneration. But you can also do like this. Okay, you connect some resistance RS here, right? Okay, if you connect some resistance RS here, and this is RD, okay, plus VDD, this is RD plus VDD, okay, and this is input here. Okay, I'm taking common source, okay, this is not given in the question. Basically, input is connected at the source, okay, and output is taken at the drain. Okay, so always keep in mind, if input is connected at the source and output is taken at the drain, so what is common, guys? The common is gate. So this is basically a common gate amplifier. What? Common gate amplifier. Always keep in mind. And common gate amplifier mimics the property of what? Mimics the property of current control current source. That you have to keep in mind always, right? Common drain, if suppose they have given common drain, right? Common, remember always, common drain mimics the property of what? Voltage amplifier. You can say VCVS, right? And common gate is given, it means it mimics the property of what? It mimics the property of current control current source. Okay, that you have to keep in mind. This is from the very basic. When we discuss amplifier modeling, we tell the examples. If you talk about BJT, bipolar junction counterpart, so common, you know, common base, sorry, 1 minute, this should be common collector, right? Common collector. Okay, common collector we have like a voltage amplifier, and common base we have like a current amplifier. Okay, so you know already that what will be the input resistance and what will be the output resistance for either of the. Okay, so in the question, and one more common you can say is common source and common emitter, right? Common source and common emitter has some sort of okay, right? Neither it will be high nor it will be low. Okay, in the range they will give input and output resistance. Okay, in the common source and common emitter, right? I mean, both will be close to each other, right? That you have to keep in mind. But in this case, here whether the input resistance will be high or high. Okay, here you see whether it will be low or high, it will be high or low, right? That you have to keep in mind. Yeah, so it is a common gate amplifier, right? So you don't have to draw any small signal model here. Okay, any small signal model here. Okay, and you can directly claim that this will be have like a current control current source. Okay, but to be able to justify more, what you can do here is, as you can see, guys, what is this? This is a, we call this as source degeneration. Okay, source degeneration. Okay, source degeneration. So if you try to find the output resistance here, right? So it will be output resistance will be some output resistance or not parallel RD, right? And here also, in this case, it will not be the same. The output resistance will not be R naught, right? Suppose this RD is also not present, so output resistance will be R naught. But if source terminal is degenerated, so your output resistance get boosted up. Okay, it will be increasing by some factor. Okay, that we will do in the regular classroom, right? So that will be the factor like 1 plus GMRS. Okay, that factor we get. Okay, so that always keep in mind whenever the advantage, whenever source terminal is degenerated, so your output resistance will be boosted up, right? So it means the output resistance will be high. Okay, so in this case also you see R1 is present here, right? And this is a common gate amplifier. Okay, and this source terminal is degenerated, right? And while finding the output resistance, we always turn off these independent sources, right? So you see, we have replaced this by short circuit, and this is a DC, so we have replaced by short circuit and everything, right? So output resistance will be high in this case, and input resistance will be low, okay, in this case, right? So you have to understand this will be what? This will be the current control current source, okay? So I hope everybody understood this, yeah? Can we move ahead? Yes, guys. See, more detailed we will see, yeah. Because see, what we are doing here is, if you know this much information, right? Okay, and if you know this, and if you understand how how CG mimics, okay, in future you will find that CG behaves like a current buffer, right? In future you will find that current, buffer. We call it current buffer, and voltage amplifier means voltage buffer. Okay, voltage buffer. Okay, so voltage buffer means what? From the voltage buffer you can't get enough voltage gain. Okay, the voltage gain will be unity. Okay, and the current gain will be high, because overall what matters in the amplifier is the power gain. Okay, and power gain is basically the product of voltage gain and the current gain, right? In case of current buffer also, we can't get whenever suppose current buffer is given and they are asking what will be the output gain, right? So you have to find the answer, and it should be very close to 1, right? Okay, and if they are asking the voltage gain, it should be high, okay, for current gain. Okay, so that you have to understand. And for current buffer, the input resistance will be low and output resistance will be high. So for this question, the option B is correct. Okay, and this is also according to the official key. So these three questions were very good questions. Okay, whatever in the classroom we have discussed directly, this was asked this year, right? And now coming to question number 22, right? What is given here is that they have mentioned the cascade of common source amplifier. Cascade of common source amplifier in a unity gain feedback configuration, right? Oscillates when, they have connected two common source amplifiers, right? Suppose this is one common source amplifier, this is one common source amplifier. Okay, common source, right? And they have connected via unity feedback. You see, this is the feedback here they have connected, right? Via unity feedback like this. Understood? So what you can see here is, what they have mentioned is that they are asking about the oscillation criteria, oscillation criteria. So what is the oscillation criteria basically? When you will study the positive feedback, and under positive feedback, you will study the concept called oscillation. Okay, we will talk about oscillator. There we always discuss one criteria, right? Because by looking at the option, they are asking about that criteria that is known as Barkhausen criteria. Okay, we call it Barkhausen, criteria. Okay, Barkhausen criteria. Okay, so what Barkhausen criteria says here is that, the loop gain. Loop gain means this. Suppose this gives you the gain A1, this gives you the gain A2, right? And the beta is already, is one unity here, right? So when you will go and find the loop gain, okay, but in the option they have mentioned closed loop gain. This is wrong actually. Okay, this is wrong. So in the answer key also they have mentioned this D is a correct option, right? But if they can remove this closed loop, right? Like if they will remove this close, okay, then all the options like yeah, then you can get the answer correctly, right? Okay, so this option will not be correct if closed you remove. Okay, okay, and this option will also not be correct, because there are two common source amplifier which are cascaded, right? So one common source will produce 180-degree phase shift, right? And one common source will produce again 180-degree phase shift, right? So total will be more than 180-degree only, and that A beta, we call it loop gain, should be greater than or equal to 1, right? For oscillation, right? For oscillation, that you have to keep in mind. Understood? And the angle should be greater than 180 in this case. Okay, so what they have given here is a closed loop gain, right? they are trying to find closed loop gain, right? So closed loop gain is greater than 1. For oscillator, let me tell you guys, for oscillator the closed loop gain is infinity. Okay, understood? Loop gain, okay, loop gain should be greater than 1, but this closed loop gain, this is actually they have, I think, some typos is there in the option. So that is why we might get MTA in the question, in this question. Okay, if somebody is going to claim in the exam like for the answer key, so they might get MTA, right? So everybody might get MTA in this question if they will consider that, yeah, there is a mistake. Okay, so option D will be correct if you consider loop gain. Okay, so Workhausen criteria only talks about loop gain. Okay, so loop gain is what if you go around this. Okay, so loop gain will be should be greater than 1. Okay, and certainly it will be greater than 1, and the angle will be greater than 180, right? According to the Workhausen criteria, if you want your circuit to be have like a oscillator, and if you want to remove oscillation, like if you want to prevent oscillation, then you have to bring some non-linearity in the feedback amplifier. Okay, so in the feed, in the basically what is there, right? Suppose this is what the basic amplifier, and this will be the feedback amplifier, right? Okay, so whenever this is under positive feedback, you will get C, sorry, this is reference input and this is out, right? So C by R, which is the closed loop gain, will be A upon 1 minus A beta, right? So if A beta is equal to 1, then this will tend to infinity, right? So closed loop gain is infinite always. So I think they should not mention like closed loop gain is greater than 1 kind of, right? Okay. So they should mention the loop gain can be greater than 1, right? I believe everybody understood this. Yeah. So in the oscillator chapter, we will go through these things in detail. Okay, so this question everybody might get MTA. Okay, marks to all, I mean to say, right? Okay, so let's move to the this question, and this question again from our classroom notes only, right? Many problems we have done, many problems from diode. In the circuit shown below, D1 and D2 are silicon diodes. Okay, they are saying that D1 and D2 are silicon diodes, and they have also mentioned the cutting voltage of these diodes, 0.7 volt, right? V in and V out are input and output voltage, and you have to find the transfer characteristic. VTC we call it, voltage transfer characteristic, right? You see the x-axis is V in and V out. Okay, so this is what the transfer characteristic. Now you have to take case one, case two, or you can go to the options, and you can also eliminate these options first of all, right? Uh, okay, so which option will not be correct, okay, and which option will be correct? So you have to take the option and the question, okay, all together, and you have to solve this question. Otherwise, you might take much time to solve this question, right? So whenever this is a practical diode, right, because they have given cut-in voltage 0.7, okay, so this diode will be on in the positive half cycle, by looking at this, suppose case one we are talking about, okay. So when V in is positive, okay, V in, when you are in positive half cycle, you can see some sinusoidal is applied here. So this D1 is on, right? When D1 will be on, when D1 will be on, when D1 will be on, when potential difference across this D1 will be greater than what? 0.7. That you have to keep in mind. What is the potential difference? This V in and this is 1, right? So V in minus 1 should be greater than 1 for D, okay? That you have to keep in mind. V in minus 1 should be greater than 1 for point, okay, greater than 0.7, okay, for D1 to be on, right? Potential difference across the diode should be greater than zero point 0.7. Then only that diode can be on. That is what the criteria is, right? And suppose that diode is a ideal diode, then you can say that what? You can say that that voltage across the diode should be greater than 0. Then only diode will be in forward bias. Right? This is case one, we call it. Right? Okay, perfect. Hmm. So as we know, V gamma is greater than point like equal to zero point 0.7. So for positive half cycle, okay, if input is like V in minus 1 is greater than 0.7, right? For diode D1 to be on, that you have to keep in mind. So from here, V in we can calculate directly. So V in will be what? V in will be minus 1, you take that side, so it should be 1.7, right? So your V in will be 1.7, then your diode D1 will be on, right? Okay. I believe this is fine for everyone. Yeah. Then what will be the output, right? If Vin is greater than 1.7, then only your diode will be on. D1 will be on, right? So now you know that your D1 is on. So you can say that, and D2 will be off for positive half cycle, right? So this is zero point 0.7 and this is V in, right? And this is what the scenario here is, plus minus 1 volt, and this is V out. Okay, so now you can directly apply the KVL, and okay, from here to here, right, plus minus, and this is plus minus. Okay, so V out will be equal to what? V in minus 0.7, that you can write directly, right? V in minus 0.7. Okay, yes. So when your D1 will be on, when Vin is greater than 0.7. How I have got directly is, we have to make sure that if any diode has to be forward bias or it has to be on, so the potential difference across that diode should be greater than the cutting voltage. That this concept you have to keep in mind. Yes. So this is one equation we have got. Okay. V out should be equal to what? Vin minus 0.7. Yes. Okay. Now, can we go ahead and talk about D2? Okay, so for second case, right? Okay, so now you come again. So for Veen, if Veen is positive in positive half cycle, so this is on, right? And now let me take the second case here. Okay, so second case, if you talk about negative half cycle, right? So this, the difference across this, suppose D2 has to be on. So what should be the potential difference? That is what the main concern is. So the potential difference across D2, okay, should be what? 1 minus Veen, this 1 and this Veen, right? So 1 minus Veen should be greater than 0.7, then only your uh, D2 will be on. So let me go ahead and write the case 2, okay? Yeah. So case number 2 will be what? Case number 2, for D2 to be on, right? 1 minus Veen will be greater than 0.7. Now, if your Veen is less than, if your Veen is less than 0.3 volt, right? If your Veen is less than 0.3 volt, then D2 will be on and D1 will be off. Obviously, it will be off, right? So you can again sketch, right? So what you will get here is, you will get, this is V in, right? And this diode is on, this time zero point 0.7, and this is V out, you can see. Okay. And you connect this resistance 1K, and there is a potential 1 volt. Now you can directly apply again, this is plus minus, and you're going like this. So your V out will be equal to V in plus 0.7 volt, right? So these are the two equations which you have got, right? These are the two equations which you have got. Okay. Now come to the come to here. Now you have found out the boundary for input, right? If input is greater than 0.7, if input is greater than 0.7, right? Okay. Then what will happen? Your D1 will be on. If input is less than 0.3, your D2 will be on and D1 will be off, right? But suppose what? If your input is, if your input is, you see, if your input is less than zero point 0.3, right? Less than zero point 0.3, or you can say in between zero point 0.3 and 1.7. Okay, that is case number 3 I will take. Case number 3 is what? If your input is between, right? Okay, if your input is between zero point 0.3 and less than 1.7 volt, right? Then what will happen? Both guys will be off. Okay, both D1 and D2 will be off. That you have to keep in mind. In that case, you see in the option now, okay, these are the two boundaries which you will get. One is 0.3, one is for input. Okay, 1.7, and between the two, if these two diodes are off, so output will be always 1. Okay, output will be always 1. So in which option this criteria is given? So first of all, C option will not be correct. Okay, straight away you can eliminate. This will not be correct. Okay. Okay, here you see between 0.3 and 0.7. Okay, you see this is 0, so this is also not correct, right? So directly you can say that option A will be correct choice. Yeah, and also everything is satisfied. Okay, so guys, look here. So I believe this solution is okay. Yeah, option A, queso, is correct. Yeah. So we have to analyze like this. Okay, in the regular classroom we will discuss more in detail. Okay, I will more explain about this. Okay, so whenever you have to check whether diode is on, you have to find the potential difference across the diode. Okay, so whatever potential is across this, you need to apply the potential more than the cut-in voltage, right? Okay, so this is V in input and this is the reference voltage, that is 1 volt, right? So we are taking the difference V in minus 1, and when it is on, we are taking the difference like this. Okay, 1 minus V in, right? We are going in the direction because D2 will be on, so current will flow from, from output to input, right? But when D1 is on, the current will flow from input to output, right? Like this. So these are the, so option A is the correct choice for this question. Okay. Okay, so now let's move to next question. Okay, so this is a question again in the examination. Yeah, okay, so great. So this is a question which was asked in the gate examination, and again in this question there is a mistake, okay, in the circuit, right? So because they have mentioned here is that the H parameter of this two port network, okay, are shown below. Definitely many students might have spent a lot of time analyzing this question because this question is not that tough, right? Okay, because if you consider this, what kind of what kind of source is connected here, guys. Again, you see this is a kind of amplifier only, because they have connected what, they have connected dependent source. What kind of dependent source is this? You see connect, you see this control para. Okay, this is V1 basically, right? Yeah, so this is a current source, but what kind of current source? Voltage dependent current source, right? Okay, voltage dependent current source they have given. If it is a voltage controlled current source, right, means the output resistance should be what? Output resistance should be high and input resistance should be high, right? According to the question I'm explaining right now, but this question has got some error, right? There should be I1 basically. I will talk about S parameter, right? S parameter, how, what are the equation of S parameter? That matrix you should know, right? So in the, according to this, input resistance means, H11 will be the input resistance here, right? I mean, okay, and this is S22. Okay, so if you see the dimension of S22 now, it will be in admittance or conductance, right? So if it is 0, then resistance will be high, right? So S22 should be 0. That is 100% sure, right? S22 should be 0. Okay, if S22 will be 0, then what will happen? If S22 will be 0, then the output resistance will be high, right? But what is the mistake here that I'm going to mention, okay, that you have to take care of? And in this question also will get MTA. So they have mentioned there is some mistake. I think some printing mistake might be there, because IIT professors are great, right? They never make mistake. Okay, only printing mistake might be there that I consider. Okay, so yeah, because they have they designed the question very nicely. Okay, and this is only the printing mistake IIT Kanpur might have done, right? So it's okay. So what is H parameter? First of all, we have to discuss H parameter. Hybrid, we call it hybrid parameter, right? We call it hybrid parameter. So we will take hybrid means, suppose we are taking V1 of the input port, so that should be I2 here. Okay. So it is given as H11, H12, S21, S22. Okay. Okay. Now here we will take I1. So this would be V2. That's it. So now we write V1 equal to H11 I1 plus H12 V2, right? And I2 equal to, okay, this equation will be applied in output port, right? And this is for input port, you can say. Okay. So because S parameter is written for two port network, so this is S21, I1 plus S22 V2, right? So if you make V2 0, okay, if you make V2 0, so H11 will be what? What is the dimension of H11? That is input resistance, right? You see I1 when V2 equal to 0, right? That you have to keep in mind. And your current gain will be I2 by I1, okay, which is S21 is the current gain, right? When V2 equal to 0, that you should know, right? And then I1 equal to 0, I1 equal to 0 means open circuit, right? So, your V1 upon V2 equal to H12, we call this as reverse voltage gain, okay, reverse voltage gain. It is not a forward gain. Basically, gain is what? Ratio upon ratio of output upon input, right? That is forward gain, but they have mentioned here input upon output, right? Okay. So you see, guys, next will be S22. S22 is what? S22 is basically I2 by V2. Okay, it has a dimension of what? Conductance. Okay, or admittance. Okay, so 1 upon S22 will be V2 by I2. Means this is the output resistance. Output resistance. Right? What mistake they have done here, you see in the circuit. Now you go back, because we should have S21 and S2, okay, S21, but they, what they have mentioned here is, guys, they have mentioned S21 V1. This is wrong, right? It should be replaced with S21 I1, right? Okay, if you apply the KCL here, okay, KCL, so you will get this equation S21 I1 plus S22 V2, right? And this is okay, right? Because you see let me show you this equation. So as h1 to v2, it is fine, right? And it should be very small, reverse gain should be very very small, right? This should be very very small, right? So H12 should be very small, always we consider, because as far as amplifier is concerned, we want to amplify, we always go from input to output, right? We don't come from output to input, right? So S12 should be 0, that is for sure. S22, if it is a current, you see, it is a current control current source. Current control current source means what? Okay, you see here, if S21 I1 we consider, so this is low and this is high, right? So according to this, option A should be correct. Okay, according to this, option A should be correct. Okay, everyone, I believe now you understood. Okay, because if they have mentioned these, this is the h parameter, so this should be the equation. Understood, guys? And in the gate examination, many students might have spent a lot of time, thinking about these options. Okay, because there was some mistake. So whenever question is given, you should write this matrix. Okay, V1 I2, okay, and check whether, you know and that too, if this question is taking a lot of time, you can also understand that there is some problem. Okay, if you are good at concept and there is a problem, right? So in this question also MTA will be there. So these are the 5 questions, guys, which we have got in the examination. I believe everybody might have understood, and we will discuss electrical engineering and instrumentation question paper tomorrow. Okay, uh, by same time. Okay, guys. So I hope you might have enjoyed. Thank you so much for today. And if you have any doubt, you can ask right now. Okay. I hope you might have enjoyed, Keso. Yes. Yeah, great. So, when we will take up this subject, we have to play with the circuit, right? We have to understand all the basics. You see, if you know the basics, you can solve any question, right? You see, There is no, we need not to give any kind of references why they are, why IIT has made mistake here, because you, if you know the concept, you should believe on your concept. Yeah. Thank you guys. So we'll meet tomorrow, right? And you know, we'll discuss electrical engineering and instrumentation. Well, thank you so much for today. Okay, so you're asking about book? Yes, yes, yes. Great question. So regarding
Sir,
book,
books
yeah,
for
yeah,
analog circuits and all. Which books do you recommend?
yeah, yeah. Sure, sure, sure. So the book which I prefer is, Donald and Neiman, right? Donald and Neiman, because that question you will find from this book, as well as I prefer second book is Razavi, okay, for amplifier, okay, basically for amplifier like MOSFET and how to play with the circuit, right? Razavi is one of the great book, and third book for diode you can refer is, in fact, Neiman is enough for everything, but you can go for Cedra, right? Cedra and Smith, and I'm talking about for gate only. Okay. Because in the gate nowadays they ask questions, what is running at this moment, right? According to the technology, right? We use CMOS, MOSFET. You can see no questions has been asked from BJT, right? But we have to study everything, all counterparts, bipolar junction, transistor as well as MOSFET transistor. Op-amp is no doubt versatile structure. So we each year we get question from this, okay. And diode, it's okay. That is very basic one. But yeah, you should know how to play with the circuit. You should know how to identify the circuit, right? What kind of circuit they have given the question, right? That is what we have to do. Then only you can score 10 out of 10 in the examination confidently, and you need not to have any kind of solution after the exam. Thank you guys. We'll catch up tomorrow. Take care.